All right, good morning, everyone. Welcome. Today we're going to present the project of measuring Tahoe's greenhouse gas emissions. Thanks for joining us this morning. We're excited to have so many people attending and that are interested in learning about this project. Today we'll be presenting the preliminary findings of the Lake Tahoe greenhouse gas inventory. And the project is led by TRPA's sustainability program in partnership with the California Tahoe Conservancy. Next slide. So I'd like to introduce myself. I'm Rebecca Kermeen, a planner with the Tahoe Regional Planning Agency. And with me today, I have my colleague, Devin Middlebrook, who is the Sustainability Program Manager. And then we have our consultant team, Ben Maritata with the Sierra Business Council, and Aaron Alvey with Spatial Informatics Group. Next slide. So we'll start the presentation with a little bit of background and context for the project, and then we'll get into the presentations on the greenhouse gas inventory and carbon sequestration pieces. We'll have time at the end of the presentation for questions and answers, so feel free to use the chat function to ask questions along the way, and we'll gather those and respond to those at the end of the presentation. Next slide. So before we get started, we'd like to get to know who's out there today. I don't see anyone, but I assume there's quite a few of you out there. And so we have a poll, and we'd like to hear from you on what type of organization or industry you represent. And the options are nonprofit, private consultant, local government, state or regional government, federal government, utility district, general public, or other. So I'll give you all a couple of seconds to fill that out. All right, so it looks like we've got our results. And the majority are local government with 23%, and a close second with nonprofit sector, and then general public at 14%, with a few others from utility, federal, state or regional, and private consultants. So thanks for doing that. Next slide. So let's go ahead and get started here. So let's talk about why we're concerned with greenhouse gas emissions and why we need to measure them. So these maps and graphs are showing warming trends across our region, with the graphic on the left highlighting the increased effects of wildfire in burned areas. And the time-lapse graphic on the right is showing a decrease in snowpack over time in the Sierra Nevada. So if you see those dark purple areas of higher snow, over time will be less. So the lighter color is showing that decline in the next 60, 70 years. And much of this change can be attributed to the emission of greenhouse gases, such as carbon dioxide, into our atmosphere. Next slide. So while these are global issues, we are beginning to see those effects locally here at Lake Tahoe. This not only threatens our environment, but our economy and our way of life. Trends that we're seeing and expect to continue to see here at the lake include a declining snowpack, rain on snow events, flooding, wildfire, drought-induced low lake levels and drying meadows, and decreased biodiversity. Next slide. Okay, so we know that emitting greenhouse gases is a problem, and we're experiencing the effects of a warming climate. So why do we need to do a greenhouse gas inventory? As a regional environmental, land use, and transportation planning agency, we need to look towards the future. We'll use the information we learn from this inventory to keep us on track and inform the work we're already doing and committed to through our Sustainability Action Plan, our Regional Transportation Plan, and our Environmental Improvement Program. We need to create resilient communities and strategies that respond and adapt. So we're setting up a regular monitoring protocol and a framework which will help us track our progress over time and adjust our climate and sustainability programs accordingly. This information will also serve our land management partners, such as the U.S. Forest Service, the states of California and Nevada, as well as local jurisdictions that are working on climate action planning. The last regional inventory we did was in 2013, and this needs to be updated with the latest and best data and modeling methods. Next slide. So what exactly are we measuring? We're measuring emissions, so those greenhouse gas emissions from the built environment, transportation, and utility sectors. We're also measuring carbon sequestration, the amount of carbon being taken up or held in our natural environment. So before we hear from our consultants on the findings of the inventory, we'd like to hear from you again on your priorities and interest in climate action. So we have another poll coming up. So this poll asks, which emission source do you view as the most important to reduce? And the options are built environment, transportation sector, utility sector, wildfire, or other. All right, so we have the results, and it looks like transportation sector has been voted as the most important to you to reduce. And that's followed by wildfire and built environment, and then utility, actually utility, then built environment, and then other. All right, thanks everyone for taking the poll. And we're gonna go ahead and pass the slideshow over to our consultant team. And we have Ben Maratato with the Sierra Business Council, who is next up.
Thanks, Rebecca. Could I just get the next slide, please? Thank you. So thanks for that introduction, Rebecca. Again, I'm Ben Maratato, Planning Technician with Sierra Business Council. And today I'm going to be going over our findings and methodologies on the sort of built environment emissions side of this project. So before we look at the actual outcomes, I'd like to take a moment just to sort of review the different methodologies that we use so that we all have some common ground when we're looking at those findings. So for the main component of this built environment side, we conducted a 2015 and 2018 greenhouse gas emissions inventory. And in that, we look at emissions from 4 different sectors. Look at the energy sector, which is primarily energy use in buildings in the built environment, the transportation sector, the solid waste sector, and the water and wastewater sector. And then within each of these sectors, it's important to note that we accounted for activities occurring within the basin that release emissions outside the basin, as well as sources that generate emissions directly within the basin. So as a clarifying example, electricity that is used within the basin is generated by combusting primarily fossil fuels at power plants that are located outside the basin, resulting in the release of emissions outside the geographical boundary of the basin. On the flip side of that, the combustion of natural gas for purposes like space heating or cooking that are occurring directly within buildings located in the basin result in those emissions being emitted from directly within the geographical boundary of the basin. And it's just important to sort of make that distinction or note that we're accounting for both types of emissions like that, so that we know that we're getting a full and holistic picture of what emissions the basin is responsible for emitting. Can you get the next slide, please? Great. So going into just a little more detail on the methodology before we look at our findings here. In our inventory, we account for the emission of 3 main greenhouse gases: carbon dioxide, or CO2, methane, or CH4, and nitrous oxide, or N2O. And then we take those three different types of emissions and report out in carbon dioxide equivalent, or CO2e. CO2e basically combines those three different gaseous emissions into one single unit of emissions, carbon dioxide equivalent, based on each gas's global warming potential, or how strongly it will affect global warming in the atmosphere. The reason that we do this is that reporting out in CO2e makes it easier to compare different emissions levels between sectors and years. So we're only looking at like one aggregate amount of emissions as opposed to three different gases and trying to interpret changes there. The last point I want to make about our methodologies, all of the emissions that were accounted for in our inventory on this side of the project were quantified using a calculations-based methodology. And so what that means is that basically we look at a GHG emitting activity and determine how much of that activity occurred in the basin. From there, we then either develop or cite from literature an emissions factor for that specific activity and multiply them together to arrive at the total emissions produced by that activity within the basin. And so then we do that across a number of different subsectors and then the larger sectors that I mentioned previously to arrive at the total emissions produced by the basin. Get the next slide, please. So with all that in mind, having set the stage on how we conducted this project, let's start to look at some of our inventory results. So first, I'll start by just sort of orienting everyone here to our different graphs and tables. So looking at the graph first, you can see that we have year here on the x-axis, and we have 2015 and 2018, the years that we conducted inventories for in this recent project, as well as 2005 and 2010, the years for which previous inventories had been conducted in a past project. And then on the y-axis here, we have metric tons of carbon dioxide equivalent, or basically GHG emissions. And so looking at the actual content of this graph, you can see that it's a stacked area chart. So each color and slash section of the chart represents the emissions from one of the specific sectors that we inventoried. So blue on the bottom here is the energy sector. Above that is transportation in red, followed by solid waste in yellow, and wastewater in green. And so the amount of area that each sector takes up on this area chart represents the amount of emissions from that specific sector. So energy had the largest amount of emissions pretty much across all 4 years, followed by transportation, then the solid waste sector, and then wastewater. So that's how we sort of read this chart. From there, I'll just take a moment to highlight some of our tables here. So this top one here, percent of total emissions, basically is sort of just a more specific quantification of what this chart is representing for 2015 and 2018. It shows what proportion of the total emissions in that year each sector made up. And then below that, in our summary of emissions table here, we break it out by sector as well as total, looking at the original inventory 2005 emissions, as well as the most recent year inventory 2018 emissions. And then at the right side of the chart, we look at percent changes in those different sectors, as well as the total from both 2015 to 2018, the years that we inventoried, and 2005 to 2018. So with that in mind, there's a couple of points that I like to make when looking at these charts and graphs, now that we're sort of all familiar with how they're laid out. The first area I'm going to focus on is the solid waste sector. So looking at the graph on the left here, you'll note that from 2005 to 2010, the proportion of total emissions that solid waste was responsible for emitting decreased substantially. You can see that by the sort of shrinking of the yellow area of the graph above 2010. The reason for that substantial change is basically a result of landfill operations. So most of the solid waste generated by the basin is sent to Lockwood Regional Landfill in Nevada. After 2005, the Lockwood Regional Landfill started to employ a methane capture system in their operations, which prevents a sizable portion of methane emissions produced by decaying landfilled waste from reaching the atmosphere, thereby reducing the emissions of the solid waste sector as a whole. So that's why we see that first initial decline in solid waste emissions from 2005 to 2010. To continue with patterns of note in the solid waste sector, if you come to our summary of emissions table on the right here, and you look at the percent change in emissions for solid waste from 2015 to 2018, you'll note that there was a nearly 50% increase in solid waste emissions. And so the reason for that is twofold. Firstly, just the amount of solid waste that was sent to landfills from the basin did increase from 2015 to 2018. But the effect of that increase was compounded by landfill operations. So I mentioned previously that the majority of waste in the basin is sent to Lockwood Regional Landfill. There is a percentage that's also sent to the Carson City landfill, which grew between 2015 and 2018. So a larger proportion of waste was sent to the Carson City Regional Landfill. And the Carson City Regional Landfill does not employ a methane capture system at this point in time. So by shifting a larger proportion of solid waste to that Carson City Regional Landfill, it also increased the amount of emissions coming from that waste landfill there as opposed to Lockwood Regional Landfill. And so that's why we see that nearly 50% increase from 2015 to 2018 in solid waste sector emissions. The last point I'd like to sort of raise when it comes to this slide here is also in our summary of emissions chart. If you come down to the wastewater sector, you'll note that from 2005 to 2018, there was a nearly 1,300% increase in emissions coming from the wastewater sector. The reason for that change is primarily methodological. Since the previous 2005 and 2010 inventories were conducted, additional better methodologies have been developed to account for other emissions from the wastewater sector that were previously not possible to calculate. And so that's why we see that sizable 1,300% increase between 2005 and 2018. With that said, it's important to note that if we look at a percentage of total emissions, even after that very sizable increase, the wastewater sector is only responsible for 0.1% of total emissions. So even though it saw that large increase within the wastewater sector, the overall total level of emissions wasn't really affected by it. So with all those explanations, context, and caveats, the main point we want to take away from this chart here is really that from 2005 to 2018, emissions decreased in the basin, or produced emissions that were basin is responsible decreased. With that said, the nominal trend that we saw from 2015 to 2018 is a slight increase in emissions. So we can get the next slide, please. Go into a few more key findings here. So like I said, GHG emissions decreased from 2005 to 2018. That decrease was just under 40% from the first year inventory to the most recent inventory. And then from 2015 to 2018, total emissions increased by about 4%. So there's not been a constant decline from 2005 to 2018. We did see a slight increase in that nominal trend from 2015 to 2018. Additionally, another key takeaway from this whole process and study is that the energy sector produces more than half of the emissions in the basin at around 59% in 2015 and 2018, followed secondly by the transportation sector at about 37%. And so those two sectors combined are responsible for over 95% of emissions in the basin as a whole. And so in future planning efforts, if efforts want to be made to reduce emissions, those are the two sectors that should probably be focused on as far as the greatest potential for reducing emissions. Not that the other sectors should be ignored by any means, but as far as just sheer volume of potential emissions that could be reduced, they're located in both the energy sector and transportation sector. Lastly, I just want to sort of highlight a point that Rebecca made earlier. What's the importance of ongoing GHG inventory work? As we continue to track emissions and see them change through time year over year, it allows us to monitor reduction efforts, as well as inform any sort of future planning efforts that we can tackle emissions in a logical and efficient manner as best possible. Additionally, I sort of touched on this in the previous slide when I talked about wastewater methodologies, but for future inventories, as methodologies continue to improve and as data sets grow more robust and granular, it will allow for the accuracy of future inventories to improve as well and allow us to get an even clearer picture of what the emissions landscape from the built environment looks like in the Tahoe Basin. Can you get the next slide, please? Okay, so now that we've sort of inventoried emissions in 2015 and 2018, what we did next is develop a business as usual forecast for future emissions out to 2045. So we highlighted the years 2030, 2035, and 2045 in our forecast, primarily because there are existing regional, local, and even statewide planning efforts that sort of line up with those years. So before I get too deep into what we sort of uncovered and contextualizing this graph and chart here, it's important to, I think, discuss what is a business as usual forecast scenario. So what this forecast scenario is looking at is basically if no future policies were enacted or implemented, there were no improvements in technologies or changes in behavior on a per capita basis, what would emissions look like into the future? Another way of thinking, so basically how we calculate this is we isolate an indicator variable for the various sectors and subsectors that we inventoried in 2018. And then we look at how that indicator variable is projected to grow into the future and apply that rate of change to the emissions from a certain subsector or sector. So for example, the energy sector is comprised of residential and non-residential energy. To forecast residential energy, we looked at projected change in number of households throughout the basin out to 2045, and then applied that rate of change to the emissions coming from the residential energy sector. So that's the general process. We use a number of different indicator variables for different sectors and subsectors to arrive at our business as usual forecast. So with all that said, looking at it, I'll give a little context for our graph and chart here. Looking at our graph, again, we have the year on the x-axis, starting in 2018, which was that most recent year that we inventoried. And then on the y-axis, again, we have metric tons of carbon dioxide equivalent or total emissions. In our chart here, we just sort of break out the numbers with detail based on sector, year. On the right side here, we have the total aggregate emissions, and on the very bottom row here, we have the net percent change from 2018 to 2045. And so with all of this, what we found, or the most significant finding really, is that under a business as usual forecast, so if no action were taken, no technological improvements made, emissions would be expected to forecast 5.7% by 2045. With that said, basically, if I get the next slide, please. With that said, we do know that there are ongoing planning efforts and future actions that could impact emissions. So, for example, in TRPA's latest regional transportation plan, by 2045, that regional transportation plan is forecasted to reduce on-road transportation emissions by 13%, or really close to 14%. On the energy sector side of things, regarding ongoing policy, we know that both California and Nevada have regulations requiring utilities to source an increasing amount of their electricity from renewable sources. Both states have fairly similar policies and goals. They differ a little, but basically by 2030, 50 to 60% of electricity should be sourced from renewable energy. And then by 2045 and 2050, 100% of electricity should be coming from carbon-free sources. So with some of the context of ongoing future action identified, potential next steps to build off of this work would be developing an adjusted scenario forecast that is able to account for those policies that we know are already in existence, that will have future impacts, as well as identifying any other local or state or federal policies that could impact emissions levels, and forecast accounting for those changes to see what future emissions would look like. Could you get the next slide, please? Okay, and so then the last component of this sort of built environment side of the project, we are conducting or developing an infrastructure of an inventory of infrastructure throughout the basin, to sort of get a sense of energy use that's occurring in different areas of the basin more closely. So using Urban Footprint, a mapping software, we developed an inventory of building energy use based on building type. So with the software, we're able to identify different the various building types and sizes located throughout the basin. And then once we've sort of developed that large data set, we apply various national average energy use intensities based on building type to get a rough estimate of potential energy use coming from specific building types and sizes. So what are the applications of a tool like this? So if you look on the left here, this is sort of a zoom in of a map of the Tahoe, of the South Lake area of the Tahoe Basin, with the different colors representing different building types or land use types. So with a tool like this, potential uses. A tool like this will enable TRPA to estimate additional benefits of some of their existing planning efforts that will require transferring development out of stream environment zones. So as that development shifts to either urban areas where potentially into newer construction, or if that development were just eliminated, or if that development were neutralized, basically what sort of energy saving benefits could be seen. And so some of our initial findings from this, from the development of this tool, about 1/5 or 20% of building energy use that's occurring within the basin is occurring in those stream environment zones. You can see at this chart here, I've broken it out just by electricity use, natural gas use, and then total energy use, just to provide a little bit of context, but they're all fairly close to 1/5. So what are some next steps with a tool like this? Thank you for skipping ahead on that slide. Apologize. So next steps for a tool like this. There are opportunities for this tool to continue to be built upon further. Using the Urban Footprint software, additional analysis modules can be run to estimate other resource consumptions types. So for example, how we looked at energy, similar analysis could be run for building type based on water use or impacts on transportation, things like that. So that's one of the next steps. Additionally, sort of similar to the general GHG inventory in 2015 and 2018, as data sets continue to improve in accuracy, timeliness, and granularity, incorporating that data into the software and into this tool will provide for more accurate estimates and a more accurate view of energy use landscape throughout the basin. So with that said, I'll take questions, I think at the end we said, but I'll turn it over to Erin now to cover the sort of landscape side of things.
Hey guys. Can you see me? Right, well, anyway, okay, cool, thanks. So this half of the presentation focuses on a novel component that TRP added to a traditional greenhouse gas inventory. one that assesses how natural landscapes can offset some of our emissions through carbon sequestration. Take note of that term, carbon sequestration. I'll speak more about what carbon sequestration is conceptually in a minute, but I would like to first provide an overview of what I'll be covering today. So besides defining carbon sequestration, I'll be talking about why we're interested in quantifying it as part of a greenhouse gas inventory, how Tahoe's forests and meadows may contribute to climate change mitigation, and how this information can be applied in planning, restoration, and policy efforts. Next slide, please. So carbon sequestration. Some of you may be familiar with this term already, but I'd like to review what it means just so everyone's on the same page for this public presentation. Carbon sequestration is part of a natural process called the carbon cycle. All life here on Earth is part of the carbon cycle. You, me, your dog, the houseplant you bought during the COVID-19 pandemic. The carbon cycle is comprised of two interwoven parts, emissions and sequestration. Throughout most of the Earth's history, emissions like carbon dioxide gas were released into the air by animals, decaying plants, and natural disturbances like wildfire or volcanic activity. And next comes the sequestration. So plants, which are functional opposite, right? They breathe out oxygen and breathe in carbon dioxide. So vegetation like trees and meadows then breathe in the carbon dioxide emissions, taking that greenhouse gas out of the atmosphere and converting it into branches and roots and soil organic matter, also known as forest carbon and meadow carbon. So the bigger the trees, or the greater number of trees on a landscape, or the more protected and sequestered meadows are, or rather, the more protected and pristine meadows are, the more carbon dioxide emissions are taken out of the air and stored or sequestered on these natural landscapes. However, the carbon cycle is out of balance right now because our atmosphere has tons of excess carbon dioxide emitted from the burning of fossil fuels, from the emissions in the built environment and other sectors that Ben just covered. So carbon dioxide is a greenhouse gas, and emitting too much of it in our atmosphere is accelerating climate change. Climate change, as we know, is leading to such unprecedented disturbances like catastrophic fire, mass flooding, all that fun stuff. And the more carbon dioxide we can take out of the atmosphere and sequester in resilient natural landscapes, and the more we can reduce human-caused emissions in the first place, the better our chances will be at combating the worst effects of climate change. So as we move through this presentation, think of forests and meadows as solar-powered carbon capture machines that play a crucial role in the fight against climate change. While Silicon Valley and researchers are in labs working on man-made solutions, we need to recognize and honor the readily available natural climate solutions, being carbon sequestration by forests and meadows, and Tahoe is blessed with an abundance of undeveloped landscapes. Next slide, please. So to quantify Tahoe's forests and meadow carbon for the 2014 to 2018 time period, which is about roughly the same time period as what the emissions were quantified for, we employed tools, methods, and data that are accessible, repeatable, and transparent. These three criteria allow folks to conduct subsequent carbon inventory updates using the same methods, so we can get apples to apples comparisons of carbon stocks to track sequestration through time. Because these methods are non-proprietary, they're not black boxes at all, they use public data and free federal tools with excellent documentation. We can be transparent about the assumptions and criteria going into these models, and then adjust them to reflect the best science as new research becomes available. It's important to understand how much carbon is in the Tahoe Basin, so we can continue to move the needle on developing a carbon accounting balance sheet and carbon monitoring indicator. I'm going to use the analogy of a balance sheet in upcoming slides. So like with finances, when you track money in versus money out, understanding how much human-caused greenhouse gas is being emitted versus how much carbon sequestration is occurring helps us to prioritize regional and local climate actions and drive investment. Next slide, please. So we need to know how much carbon is currently sequestered what our carbon stocks are for the basin's natural areas. I'm going to focus first on forests, and then I'll switch to meadows. Then I'll bring it all together in a snapshot of a carbon accounting balance sheet. So next slide, please. We quantified forest carbon stocks in 2014 and 2018 for the entire basin. Here on the screen, we visually mapped preliminary results of forest carbon stocks, zoomed into the southern shore so you could see the granularity better. So warmer colors equals lower carbon stocks, less carbon sequestration, and cooler colors equals higher carbon stocks. We use the same units as what Ben at Sierra Business Council presented earlier in the emission part of today's presentation, just so we can have that comparison. You can, in the map here, you can see that there's been an overall increase in carbon stocks, potentially an overall increase in the number or size of trees on the landscape in this 4-year snapshot. So on the left, you have 2014, and then for the same frame, you have this carbon stocks on 2018. And for example, you could see the gradual forest recovery in the Angora fire burn in the lower left or lower right-hand corner. So the basin's forests as a whole have had net growth, despite accounting for trees that have died or fell down, or any fuels reduction treatments that occurred during this time period. Next, we'll look at meadow stocks. Next slide, please. So, like forest carbon, we quantified meadow stocks for the entire Tahoe Basin using publicly available data and the best data sets available that have full coverage across the basin. Here on the next slide, please. Here on the screen, we visually mapped preliminary results of meadow carbon stocks, zoomed into the South Lake Tahoe area so you can better see the data. This map of meadow carbon stocks has the same symbology and visualized unit thresholds as the forest carbon map we just saw. So warmer colors equals lower carbon stocks, cooler colors, the purples, the blues, equals higher carbon stocks. Next slide, please. In all, there are about 5,000 acres of meadows in the Tahoe Basin, which results in over 200,000 units of carbon stocks. And meadows have the potential to play a super important role in carbon sequestration, but their ability to sequester carbon is influenced by meadow condition, whether it's pristine or degraded. According to recent research by Sierra Nevada's own Cody Reed and Amy Merrill, a pristine meadow has the ability to sequester a lot of carbon, which is awesome, because the more carbon there is for a meadow, it doesn't increase the risk of catastrophic wildfire. However, a degraded meadow actually releases a lot of emissions back into the air, doing the exact opposite of what we really need them to do to battle climate change. Meadow condition, whether it's pristine or degraded, is really hard to assess just by looking at it. There are some indicators of meadow health, but we really need to incorporate measuring meadow carbon and analyzing soil samples. This includes a field and a lab component into our restoration efforts to better understand meadow carbon flux dynamics, and therefore have better numbers for our carbon accounting balance sheet. Slide 6, please, or next slide, please. Which brings us to our accounting snapshot for 2018. Please note that these are not absolutes. Both emissions and sequestration are a stochastic dynamic process, and there is uncertainty in both of these data sets, but it's using the best science we have currently available. In a traditional financial accounting balance sheet, you track money out versus track money in, and it's bad if you spend more than you save. On the screen here is an example of a carbon accounting balance sheet, which tracks greenhouse gases out versus carbon sequestration. In red, we have our 2018 greenhouse gas emissions going out into the atmosphere, accelerating climate change. Like in an accounting ledger, red means bad. In green, we have our 2018 carbon sequestration, which is essentially vegetation growth, taking that greenhouse gas out of the atmosphere. Green is good. So if we compare the values out versus in, we see that for 2018, there are actually more emissions in Tahoe that were released than what the basin's natural areas were able to sequester. Hence, we still have more work to do to combat climate change. Next slide, please. So in sum, the takeaways from the carbon sequestration portion of this presentation are that it's really important to reduce emissions. We can't sequester our way out of climate change without significant effort to reduce emissions. This is especially true because forests and meadows can't continually increase in carbon sequestration. It's impossible nor appropriate in this region to add more and more trees to the basin. Trees also have a lifespan, and carbon sequestration plateaus as the forest enters a stable state, which is good for resilience, but doesn't allow us to infinitely increase the amount of carbon sequestration occurring each year. And yeah, so forest resilience influences the ability to offset those emissions. Right now, we potentially have more carbon stocks on the basin than we historically did because of, as a result of fire suppression. So that sets us up for, well, you know, in the short term, we might have more carbon sequestration. In the long term, that could cause a catastrophic wildfire, thereby releasing all those savings back into the atmosphere. And then another point is that meadows have the potential to be a really important carbon sink. However, they're a resource that California is quickly losing. And more research is needed to understand meadow and soil carbon flux. We need long-term standardized monitoring integrated into not only our restoration efforts, but data-driven policies. Our example snapshot of carbon accounting is not the full story of carbon and climate trade-offs, but it gives us good insight into 2018 values that are helpful for providing data-driven goal setting. Next slide, please. So we can apply these takeaways in a variety of ways. We can use the carbon stocks to assess and accelerate forest resilience, to figure out where and how to assess and accelerate forest resilience and fuels reductions programs, which then allows us to access state and federal funding. California Natural Working Lands, the Tahoe Central Sierra Initiative, Lake Tahoe West are all efforts that are going on to figure out ways to increase the pace and scale of restoration, of helping Sierra Nevada become more resilient in ways that account for socioeconomic factors as well as the environmental factors. And these efforts are also trying to predict how land management trade-offs and climate change, through forecasting might be able to affect carbon sequestration among other factors like wildfire resilience and watershed health. Secondly, improving our understanding of climate science, identifying what gaps there are and what research or development is needed to help us close those knowledge gaps so we can maximize the effectiveness of regional and local climate planning and policies. So for a start, it would be good to increase our understanding of meadow carbon so we have a better understanding of how to restore them, to maximize the potential for them to be carbon sequestration sinks rather than carbon sources, releasing it back into the atmosphere. So to prioritize restoration, we could obtain a rough estimate of which meadows might be sinks versus sources by crosswalking the Tahoe Aquatic Resources Inventory with existing meadow condition categories and pairing these results with the recent stream environment zone assessment that was recently conducted for the basin. But either way, we do need long-term monitoring and standardized procedures to track carbon and carbon flux over time in both meadows and forests and soil. Lastly, we can try to expand the forest carbon offset market or the carbon offset market. Currently, California has its own market-based approach to cap and trade. It's basically conservation financing where landowners are paid for their forests and other methods or techniques that try to keep more carbon stocks on the land instead of having those released into the atmosphere. And California is a state program, so it can't control the federal lands that mostly comprise the basin. So if we're able to, as a nation, recognize that carbon sequestration is really important in our fight against climate change, and expand the carbon offset market to include federal lands or other carbon sequestration methods, then that will allow more folks to get paid for your carbon sequestration contributions. Placer County has its own offset market too that they're developing. And so, this market can happen both on the federal, regional, or even local level. And yeah, so now back to TRPA with next steps for the climate program.
Thank you, Erin. Thank you, Ben. So we're going to move on to the question and answer session. And I'd like to introduce our panel. We have Devin Middlebrook, who's the Sustainability Program Manager with the Tahoe Regional Planning Agency. We have Ben and Erin, whom you just heard from. And then also joining us today is Nadia Tace. She's a Senior Environmental Scientist with California Department of Forestry and Fire Protection. And she's been working with us on this project as part of our steering committee. So thank you all. And I'll just go ahead and pull up some of these questions. Okay. So one of the first questions we were asked was how much greenhouse gases our emissions were produced from wildfires. And I'm not sure that we measured that, but maybe Ben or Erin can respond to how we would measure emissions from wildfire.
I can talk a little bit about that. So the emissions from wildfire, so let me just clarify that dead trees do store carbon, just not as much or for as long as live trees do. However, the way that we typically quantify emissions from wildfire, at least in terms of carbon dioxide emissions, is looking at what was on the landscape versus what is, post-fire on the landscape. There's also some models and assumptions that could be made about the efforts to fight the fire, as well as what the emissions are from the actual smoke itself as well. So there's standards and procedures that do try to look at emissions and quantify them, and that does dovetail too with public health and air quality monitoring as well.
Do you want to add something to that, Nadia?
Yeah, I was just going to add, I think we're hoping to get that information in the final report. And as a comparison, I work on a statewide inventory, and we do have some data for the National Forest System lands in the basin, so just the Lake Tahoe Basin Management Unit boundaries. And we actually show very little emissions because of what Erin mentioned, in that, when we have a fire, the carbon that's burned from the live trees, actually, a lot of it transitions to the dead pools. And so we don't actually always see a huge net emission to the atmosphere. And we, in the basin, the fires that we have are very dramatic and very large, for our context, but on the larger landscape, they are actually quite small. And we do really good at fire suppression here. So our fire emissions in the basin are not as large as you might think they would be.
Great, thank you. So our next question, I would probably ask this question to Ben. For modeling the building emissions in the Tahoe Basin, can you use billing data for electricity use and natural gas?
So if that's referring to like using actual existing data, like real data as opposed to national averages, I guess. So we're looking at some potential of taking the aggregate sort of energy use that we collected in our inventory and trying to apply that or merge that with the urban footprint methodology using national averages. That's still in work in progress to see if that's feasible or the findings are valid and significant. But as far as like collecting individual building data, that's something that's not feasible when it comes to energy use, just because of privacy concerns. That's not data that's made available.
Thanks, Ben. So our next question is about meadows. And the question is, can we have an example of a local pristine meadow versus the local degraded meadow? And I think we did have that on one of the graphs, Erin. So maybe you can speak to that and how that measures out.
Yeah, so in the figures in this presentation, it's more about carbon stocks based on assumptions. We use the best data sets available, but even then there's still uncertainty within those data sets on how, those assumptions actually are materialized in reality, like how pristine or degraded that meadow actually is. So it's really hard to visually assess just by looking at it how degraded or pristine a meadow is. There have been really great restoration efforts along the upper reaches of the Truckee River, so Johnson Meadow, then also Pope and Baldwin area, the Taylor Creek Meadow, yeah, but there are some indicators that we can crosswalk to get a rough idea of meadow pristineness. That would be, whether or not they have facultative wetland or riparian plants in those plant species in those. How incise the channel might be. So there's different metrics, and some of them are captured in the Tahoe Aquatic Resources Inventory, as well as the Stream Environment Zone assessment that was recently conducted. However, it's more than just how wet a meadow is. It takes into a broader context, all those subterranean layers as well. And then also conifer encroachment and how climate change might be drying out meadows or not having meadows as wet as long. So, we can't just take an initial snapshot, look one day at the wetness or something and see how pristine it is. It's really a cumulative effect.
Yeah, and I think that the recent SEZ Stream Environment Zone assessment does have some findings that we could crosswalk with this study as well. And I think that's what's exciting is the future, application of looking at the benefits of restoration and looking at what we consider a degraded meadow, and then also the carbon sequestration benefits of that. All right, so our next question, let's see here. This is kind of a technical question, so we'll see here. Would you consider adding a consumption-based solid waste inventory, which estimates greenhouse gas emissions from the complete life cycle of materials consumed in the basin beyond just end-of-life impacts at landfills? Some emissions might be emitted outside the basin, but include the complete life impacts of materials consumed here, like production and transportation impacts.
Sure, I can address that one. So there are some methodologies for sort of consumption-based inventories. There tends to be much more uncertainty in that type of inventory, especially on a jurisdictional, or in this case, multi-jurisdictional scale. They're more effective for in say a specific organization scale. So like one company or even one location of a company's business is where those more make sense. With that said, regarding life cycle, regarding transportation at least, that is accounted for in some component in the inventory methodology that we use. So far in at least the trips that are being made to transport those consumable products into the basin and then out of the basin to the landfill are captured in the transportation sector of the inventory. So we do touch on some of that. There are obviously additional life cycle emissions that we're not accounting for though, because just the methodologies don't really exist at a high quality level for this scale of inventory.
I think that the system boundaries are important to consider here. Some of those emissions from those life cycle processes are captured in other sectors, or and at the statewide level or at the national level, and so we want to be careful about not double counting emissions. That kind of information is certainly helpful for understanding our carbon footprint as this region. But in terms of inventory, those system boundaries get a little wonky when you start getting into life cycle impacts. And, you know, with the statewide greenhouse gas inventory, we do have many more sectors covered. And some of the work that I'm also doing with the state, we are trying to look at more of a life cycle approach with wood products in particular, and looking at consumption and imports and exports into the state of California. But again, when it comes to inventorying that, we have to be careful about our system boundaries. But we do want to understand those types of questions so that we can make better decisions with what we're consuming.
Great, thank you, Nadia. So it looks like we're just about out of time. So those questions we don't get to right now, we can send those out, questions and responses as notes, and have those available through TRPA. So feel free to reach out to Devin and I, and we'll provide that information. So I'll go ahead and let Devin wrap up the presentation and next steps.
Yeah, thanks, Rebecca. If you want to go to the next slide after that, yeah. As Rebecca mentioned, the Tahoe Regional Planning Agency and Basin Partners in 2014 developed the Sustainability Action Plan, which set the direction for climate action in the Tahoe Basin. We also have long worked on climate change through our regional plan and regional transportation plan, reducing emissions. And that plan has guided, as you saw from 2005 to 2018, has guided a decrease in emissions, greenhouse gas emissions within the Tahoe Basin. Building off of that plan and the science and planning efforts that have taken place since then, including things like the Tahoe Truckee plug-in electric vehicle readiness plan, the California Tahoe Conservancy's vulnerability assessment and upcoming climate adaptation action portfolio, and a whole host of other things. The partners in the Tahoe Basin, including the Conservancy, United States Forest Service, then the states of California and Nevada, and local jurisdictions such as Placer County and the city of South Lake Tahoe, are all very dedicated to working on and addressing climate change, and will be over the next year working on creating a climate resiliency framework for the Tahoe region that takes state and local policy, projects, programs, goals around climate, and brings them to a regional scale to further advance our efforts. Next slide. This will, again, as I said, support statewide climate goals and be informed by the greenhouse gas inventory. I think Ben highlighted a great example of why we need to have regular greenhouse gas inventories with the landfill waste and the methane capture. Knowing that data on the back end, we can now work with our partners in the basin to address that and work on reducing those emissions and really focusing on the infrastructure, that built environment piece, electricity and gas usage, transportation, which through our regional transportation plan, which is currently being updated and the final plan being released soon, that will address transportation emissions, and then natural resources through the environmental improvement program, which has already invested over $2 billion in restoring Tahoe's environment. We can strengthen the climate connections such as meadow and SEZ restoration, all while identifying and addressing regionally significant priorities and engaging local communities because we're all in this together. Next slide. So thank you all for coming to this webinar and tuning in. We will be sending out notes, slideshow, and recording afterwards, and stay tuned for more ways to be engaged in climate action at Lake Tahoe. Have a wonderful weekend.